Hi guys, this is Charles 2 and this is my Physics 2212 Lab 3 with circuits. The purpose of today's lab is to observe and predict a circuit's behavior when it contains resistors and capacitors when they are in series or parallel. Some things to know beforehand. Ohm's law, where V equals IR, the node rule, which says the current into the node will equal the current out of the node. The loop rule says the sum of the electric potential differences around the loop is zero. And then capacitance C equals Q over delta V, or the change in potential difference. And then the system will be the circuit and the surroundings will be everything else. Some assumptions: the wire has no current and there is no resistance in the ammeter. So for our first experiment, we had to model this right here, where I had two 1.5 volt batteries, two resistors, one with 47 ohm resistance and one with 100, and then we had two ammeters, one up here, one down here. We were told to find the current. As you can see, we found the current to be 0.02 A. Yeah. Okay, so the second part of the experiment, we had to replace one of the ammeters with a voltmeter. And as you can see, the delta V became 3 and the current became 0. That is because this voltmeter acts as like a switch. And then we had a basically find the potential difference across different parts of the path using a voltmeter of this model right here. And based on a voltmeter, I got like -3 for A to B, 0, 0.96, 0, 2.04, and then 0 for the rest. And if you add them all together, you get a potential difference of 0, which matches what the loop rule says, where the potential difference will all add up to 0. And then we graphed it right here. Yeah. For the next experiment, we had to make an RC circuit with the 9 volt battery, 200 mF capacitor, and then a 10 ohm and 20 ohm bulb. So my observations was, when it was connected, the 10 ohm battery, the 10 ohm bulb starts really bright, but then it decreases until the current equals 0. Then when you disconnect the battery, the bulb will then light up again, but then it began to fade. Yeah, and then the time it took, it was like around 6.32 seconds to charge the 10 ohm bulb, and then 6.54 to discharge. And then the next two are for the 20 ohm bulb. So you can see they're generally the same time. Yeah. And then here's the time, here's the delta V of the capacity, and then this is what happened. Well, this is what the graph looked like when I had ln delta V over the initial delta V, and then time on the other axis. Got a slope of -0.1697 for that graph, and then 1 over RC is equal to, so then you get 5.892, then 30 times 0.2 is 6. You can see that the numbers are very close. Yeah. So what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real one, and how would you have affected the circuits you hooked it up to? Well, in real life, an ammeter would have a resistance that would be greater than 0, which would cause the current to decrease. What if you were doing this experiment in real life and use a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor reach full charge? Would this prediction happen in real life? It would charge it really quick because it would go directly from the battery to the capacitor, but there would be some delay to the wires. Okay, bye.